Okay, 3.2 measures of variation. We just got done talking about measures of central tendency, mean, median, mode, which are all talking about the middle. A measure of central tendency talks about middle, while measures of variance talks about how spread out the data is. The one that you've probably talked about before in an Algebra 1 class or maybe a middle school class would be range. Now that's just your largest value minus the smallest value. Only two sets of data are used in the computation, so much of the information of the data is lost. So here's the idea that you could greatly affect that by taking an extreme data set. So you could have an outlier at the very top or at the very bottom, and you come up with a range that's totally not realistic. But here's an example of my range. I got my data set here. The largest number is 18, the smallest number is 10, so my range is 8. Okay, a more accurate way of looking at spread of data is your standard deviation. The standard deviation and variance measure the spread of the distribution, and it's centered about the mean, and we'll use it around the mean in like other instances, not so much now. Okay, but the formula for calculating standard deviation and variance are just really close to each other. They're slightly different when you're dealing with a population or a sample. Now I'm going to talk mainly about sample right off the bat because that's the one we're going to use the most. But if you notice that this underneath square root stuff is the same thing as the variance formula, that's because if you have the standard deviation, you can square it and you'll get the variance, or you can square root the variance to get the standard deviation. Now there's some Greek symbols in there that I'll explain here with a little bit of table work here coming up. But here's kind of the steps of my table work. I need to find the mean of the sample. Well, since it's a sample, I'm going to use the sample mean formula. And the little n means the number of pieces of data, and that capital E sigma means to sum up. The x is just all the data. Subtract the mean from each of the data points. Okay, these are your deviations, so how far away they are from the average. Some of them will be negative, some will be positive, some will be 0. Next, you're going to square those numbers. I'm sorry, here's the x minus x bar. Next, you're going to square those numbers. And then finally, you're going to sum them up. Okay, so now that's the numerator of your fraction. Then you're going to divide by n minus 1. Now right there is your sample variance. If you want the sample standard deviation, take the square root of that, and there you go. So here's my example. My set of data would look like this right away: 2, 3, 3, 8, 10, and 10. There's 6 numbers. If I add up those numbers, I get 36. So the sample mean is the sum of the x's, 36, divided by how many I got. So you'll notice in my second column, I have each of the original data, 2, 3, 3, 8, 10, and 10, and I'm subtracting 6 from all those. Now, it's okay that I get a -4, -3, and -3. That's going to happen. No worries, because I'm going to take and I'm going to square that number. So -4 squared is 16, -3 squared is 9, -3 squared is 9, and so on. You can see those sum or values. Okay, but all these numbers become positive. I add them up and I get 70. Well, this piece right here is the numerator of my fraction for standard deviation. So there's the 70. N minus 1, so 6 minus 1 is 5, get 14. There's my variance. Take the square root of that, and there is my standard deviation. Okay, so just to check that again with 3 numbers, and what I'll ask you to do is do this with the small sample size. But I got my mean of 26, so I'll take each of my numbers minus 26. Again, some are positive, some are 0, and some are negative. If I add these up on accident, my sum will always be 0. That's bad. Okay, you need to go through and you need to square them first. Then when you square them, you sum them up. There's where you get that numerator of 32. The 3 numbers, 3 minus 1 is 2, and then you get a variance of 16. But if you take the square root of that, there's your sample standard deviation. Okay. Here's another possible formula you could use. I stress the computational formula, but you can use the computation formula. Just a little bit different work. Notice that there's a sigma of x squared, and there is a sigma of x, and then you square it. Those are not the same. So here's my original set of data: 4, 5, 5, 7, and 4. I have to come up with the sum of x's, and then I just take each number and square it and get the sum of x squared. Okay, so there I got my sum of my x squareds. That's the first number I see, 131, minus 25 squared over my 6, all over 6 minus 1, and then take the square root of that to get my standard deviation. Now, if I take 25 squared, that's not going to be the same thing as 131, so that's how the sum of x squareds, this guy right here, is not the same as that term. Okay, so I like to work with that fraction first. 131 minus that answer divided by 5, and then take my square root. And my standard deviation is approximately 2.32 if I round to the nearest 100 spot. Okay, here we go. We got population ones as well. Just kind of note that they're in the Greek letter form instead of that. So I have this lowercase here that well, it's lower sigma is what it is, but it's population variance. The population standard deviation formula in the book looks something more like this, where it's got mu this time and then over a capital N. Okay, N is the same thing as lowercase n, it just means that it comes from population. There is no computational formula for population variance and standard deviation, so you have to use this one if you're going to do it by hand. Okay, so how do you know how spread out your data is? Well, you look at two things. Not only the standard deviation, but also the mean. That you can put them together as a percentage. It's this number called the coefficient of variation. It's difficult, again, to compare standard deviations if you really don't know the reference or the units. Like, for example, I could be using variation for temperatures in Celsius versus variation of temperatures in Fahrenheit. There are two different ways of measuring, so I'm going to come up with two possible answers. So, coefficient of variation for your two samples and populations basically work out to be the same. It's just that it's S and X bar versus sigma and mu. Same process. You'll take your standard deviation divided by your mean times 100. Okay. The smaller that number is, the more consistent they are. The bigger that number is, the more variable they are. So if I have a sample of infants with the mean weight of 6.2 pounds and a standard deviation of 1 pound, I'll go 1 over 6.2 times 100. So 1 divided by 6.2, and I get 16.1%. Okay, my other standard deviation of 1.5 in this 3-month sample over 10.5, and then multiply that by 100 and get 14.3%. If I rounded to the nearest 10th, I should have been to the 100th, but whatever. Okay, which one has more variability? It would be the newborns. And what I mean by variability is kind of, in a way, out of control or spread out. And I say that because 16.1% is bigger than 14.3. Now, that's not a drastic difference, so it's not as big of a deal. All right, kind of a long section, but I get it. The last thing I want to talk about is this theorem called the Chebyshev's theorem. It says that for any set of data and for any number k greater than 1, the proportion of the data lies within k standard deviations of the mean is at least 1 minus 1 over k squared. Okay, so like k standard deviations means that on a number line from the mean, so if I were to put the average right here and I were to count up 1 standard deviation and 2 standard deviations, I would also do the same thing in the opposite direction. That right there is 2 standard deviations away from the mean. That means that at least 75% of the data would fall between those two numbers. And if I want 3 standard deviations away, I put in 3 for k. In fact, I should back up a little bit. That 75% came from the fact that if I put in a 2 for k, I get 1/4. 1 minus 1/4 is 3/4, and there's 75%. 1 minus 1/9 is 8/9, which is 88.9%. 1 minus 1/16 is 15/16, so 93.8%. That's for 2, 3, and 4. you can go beyond that with 5 as well. Okay, so let's say a math class completes an examination and has found that the mean is 77 and a standard deviation is 6. According to Chebyshev's theorem, that means between two values, or what two values would be at least 75% of the grades be. So since it's 2, I'm going to take the mean right here, put it in for x bar in both cases. I'll put in my 6 here for s, multiply it by 2, do some subtraction and adding, and get 65 and 89. And what that means that at least 75% of those test grades lie between 65 and 89. Yeah, so there you go. There's some problem sets you can work on. Do as many you like. They're all odds. And I'll show you a little trick to do this a little bit quicker on your calculators tomorrow.